Hello and welcome to today's webinar. My name is Dana Ollendyke and I'm the project manager for the Penn State Extension Energy team and also a member of the TOPCORP training team. On behalf of the TOPCORP team, we are very grateful to have Mark McClure here with us today to speak about geothermal energy.
All right. Thanks very much for.
Give me 1 second, Mark.
Go ahead, Dana. I thought you were introducing
This
me.
webinar is hosted by TOPCORP, which is a consortium of universities that deliver oil and gas regulator training. Our consortium includes Penn State Extension, the Colorado School of Mines, and the University of Texas at Austin. TOPCORP's mission is to train regulatory oil and gas field inspectors and policymaking personnel, as well as provide technical knowledge, growth in professional networks, and an increase in participants' confidence. We train regulators in the US and Canada, and we continue to expand our curriculum to include offshore aspects of oil and gas operations. Here you will see a listing of all of our groups and businesses that help support TOPCORP. Thank you so much for your support, and we couldn't do this without you. Before we get started, I just wanted to mention some housekeeping items. Use the chat pod to introduce yourself and the Q&A pod to ask questions during the webinar. If there is time after the presentation, we will ask those questions of our presenter. This webinar is being recorded, and you will receive an email in about 3 business days with a link to the recording. You can also visit the Top Energy Training website for past webinar information. Lastly, if you have any problems during the webinar, please email me at the address below. Let's get started. Thank you again, Mark, for joining us today to discuss geothermal energy. Mark is he established ResFrac in 2015 to help operators maximize value through the application of advanced geomechanics and reservoir simulation. Before founding ResFrac, Mark was an assistant professor at the University of Texas at Austin in the Department of Petroleum and Geosystems Engineering. Mark, please take it away.
All right. Hello, Dana, and thanks very much for inviting me to speak today, and glad to be joined by so many participants. My goal is I'm going to talk until about 45, so 12:45 Eastern time, and leave about 15 minutes for questions. And what I'd like to do is tell you a little bit about geothermal energy. I'm going to give you first an overview of geothermal, and then I'm going to talk about 2 fairly recent projects that have had very, very exciting and promising results related to geothermal, and that offers the hope for greatly increasing the amount of energy we produce from geothermal. Finally, I'll finish up with induced seismicity, which has been an occasional issue for geothermal and for enhanced geothermal systems in particular, and try to give kind of a very, very brief primer on that topic. So first off, when we talk about geothermal energy, it's important to understand that that can be used to refer to different types of things. So especially in the Northeast, if you hear geothermal energy, you might be thinking about shallow ground source heat pumps that's installed just in your backyard and to help heat and cool your house. That is absolutely geothermal energy. However, it is not what I'm going to talk about today. I'm going to talk about deep geothermal energy, which is primarily used for electricity generation. So to just kind of skip ahead to that, here's a schematic of conventional geothermal energy. We are going to produce very hot water from the subsurface. So a typical geothermal well might be producing at 400 degrees Fahrenheit or hotter. Sometimes they might go down to 300 degrees Fahrenheit. So obviously that's very hot. That's as hot as your oven. As you go deeper into the subsurface, you get closer to the Earth's core, the temperature of the rock, of course, goes up. That so-called thermal gradient is highly variable from place to place. So out here, I live in California. In many places in California or in Nevada, the thermal gradient is relatively high. Actually, on the East Coast, the thermal gradient tends to be relatively low. So a well that's drilled a mile deep in California might have a very different temperature than a mile deep in Pennsylvania, or even actually in California's Central Valley would be very different from a mile deep closer to the coast. So generally speaking, of course, drilling deep is expensive. And so when we want to produce geothermal energy, we're going to go and try to find places where the earth is unusually warm or that thermal gradient is unusually high. The most the hottest places we can find are places that are above magmatic intrusion. So it's associated with volcanic activity. Um, and in fact, that is where most geothermal, major geothermal power plants are producing from is some kind of formation that's above some sort of magmatic intrusion from the subsurface. Just to put these temperatures in perspective, um, if a typical oil and gas well might be drilled to 5, 10,000 feet depth, but a typical oil and gas well might be at 200 Fahrenheit, 250, maybe 350. When we go to these geothermal wells that are 350, 400, 450, 500 degrees Fahrenheit, these are in fact hotter than all or nearly all oil and gas wells. So that is an important distinction to make, which means we either need to go deeper or we need to be in very specific places where we can find these sorts of um, geologic conditions. And it may not be a surprise to you that the hottest known geothermal regions are places where there are plate boundaries and natural volcanic activity. So, along the west coast of the United States, there is a boundary between the Pacific Plate and the North American Plate. Subduction has occurred at Pohang, part of that continental, barrier. There's a strike slip, a fault that runs up and down California. All of that is associated with a lot of volcanic activity, and that runs all the way down the entire, South America and the whole Ring of Fire. So places like Iceland, which of course is essentially a volcanic island above a hot spot. So places like Iceland, California, South America, Indonesia, the Philippines, Japan, parts of Alaska. Those are even in Hawaii. There's geothermal production. There is not geothermal production happening in the East Coast of the United States, at least not the type that I'm talking about, the sort of deep production for electricity. Um, because the thermal gradient is much lower. We're kind of in the middle of a continental crust or continental plate there. And so you don't have that kind of concentration of temperature at shallow depth. Having said that, there are people who are looking at figuring out ways to do geothermal in places with lower thermal gradient. That would involve drilling deeper. So that is absolutely a possibility for the future. And of course, there's things like ground source heat pumps. So let's first just talk about conventional geothermal. This is kind of what we're usually talking about when we refer to geothermal energy. So we have a magmatic intrusion. It is extremely hot. It is heating up the fluid in the subsurface. So actually, when you go deep in the earth, the rock always has porosity, which means it's kind of like a pile of sand. You can pour water into a pile of sand, and water will actually flow through that pile of sand. So similarly, all rock, or nearly all rock, has at least a little bit of capacity to store and conduct fluid through that subsurface. And so as a magmatic intrusion is coming up, it's heating up the rock above, heating up the water that's in that rock, and that water will tend to rise as it becomes hotter and less dense, and so it becomes buoyant. And what we need for a conventional geothermal reservoir is for that hot water to rise and then at some point hit a layer of rock in the subsurface that is impermeable. And that hot water will be unable to continue rising. It will hit that cap rock. And then actually what will happen is it will kind of recycle. So you'll see the hot water come up, come kind of laterally along the cap rock, and then actually cycle back down again, and it cycles. And that's how you develop these kind of relatively localized, very hot regions of the subsurface. So there are places you could drill down 2, 3, 4,000 feet and see fluid that's 400 degrees Fahrenheit, which is much hotter than a normal thermal gradient. Um, Now, an important thing for people to understand about geothermal is that we can make electricity from this hot water or the steam that comes out of these wells, but it requires a lot of production. So a typical oil and gas well, if you were producing 100 barrels of oil per day, that would generate a good amount of revenue, right? A few months ago, the price of oil was, $60 a barrel. Today, it's 100. So 100 barrels a day would be today's pricing closer to $10,000 of revenue a day. That's a good revenue, and of course, adding that up over many days and years, you could make a lot of money off an oil and gas well. For geothermal, the economic value of 1 barrel of hot water is significantly lower. There's literally less energy stored in a barrel of hot water than a barrel of oil. Also, it is in actually a less useful state. It's harder to store and transfer into useful work. And so as a result, we can make electricity, we can generate revenue and power and energy from geothermal, but we need, for economic purposes, we need very high flow rates. So a geothermal well that produced 100 barrels a day would be a a dud. You would not even bother. You would just shut that well in and plug and abandon it. So another requirement for conventional geothermal is not only very hot rock, but we need very high permeability. And permeability refers to this idea that we can flow fluid through the rock. And the higher the permeability, the easier it is to flow that fluid, and the more rapidly it will flow. So that combination of things, we need high permeability and high temperature. That is a kind of very special set of geologic conditions that is not present in most places. So if you have that happy coincidence, you can drill a well down 5,000 to 10,000 feet, and then when you open it to flow, you will have enormously high flow rates of hot water and steam coming out of the well at very high temperature, and you can utilize that energy. But in most places, you don't. And so that's actually been the primary limiting factor for adoption of geothermal energy is there aren't enough places around the world where we have all of these conditions already in place. Now, I'll talk about in a few minutes technologies that are being developed to overcome that limitation, but that is the limitation of conventional geothermal. So you have a well, you're producing not hundreds, but perhaps thousands of barrels a day of very hot water or steam. We often don't use barrels per day units in geothermal, but that's an oil field unit. And we're going to take that hot water or steam and generate electricity. Because yes, there's a lot of energy in this fluid that we produce, but we also need to sell it. And so what is the useful product that we can sell from a lot of having a whole bunch of hot water? Well, one thing we can do is we can take that hot water and steam, we can put it through a power plant, generate electricity. And obviously, that is an economically valuable product. Now, there are other applications. Let me skip ahead here. There is direct use. So in addition to generating electricity, very hot water from the subsurface can be used for other purposes, used in hot like spas and resorts, aquaculture, district heating, space heating, greenhouses, and other industrial applications. So direct use is also used, where we just take the hot water and we directly use that heat for something. But I would say the majority of the economic activity around geothermal energy, excluding ground source heat pumps, is for electricity. And this plot is very important. It shows the efficiency of electrical conversion from the reservoir heat into electricity. And these efficiencies are fairly low. So what we see is as the reservoir fluid that we produced becomes hotter, then it becomes more and more efficient to generate electricity. And that's a general statement. Generally, the greater the heat of something, the more efficiently that energy can be turned into work, into electricity. When you burn natural gas or you burn coal, they burn at very high temperatures. And so that actually means that the efficiency of the power plant can be pretty good. You might hit 50% or more. With a geothermal power plant, that efficiency is lower because the temperature is lower. We're producing at 3, 4, 500 Fahrenheit, not 2000 Fahrenheit. So that's another thing to keep in mind. And this also illustrates why we can't just trivially do geothermal everywhere, because if we drilled somewhere, so reservoir enthalpy, 850 is around 100 degrees Celsius, or 212 degrees Fahrenheit. So if we drilled into a formation that's basically below the boiling point of water, the efficiency of electrical conversion is so low that it's not likely to be viable. So that's why we need to target these hotter formations where we actually can efficiently generate electricity. So as I said, we need special geologic conditions. That's where it's found, is around volcanically active areas. Now, here's a different map. This is a map of the temperature at quite significant depth, 6.5 kilometers depth, across the United States of America. And so you can see how drastically different temperatures are between the East Coast and the West Coast. So out here in the West Coast, this is, for example, Nevada is in the Basin and Range. This has been affected by a lot of tectonic activity. So we have quite elevated thermal gradient across much of the western half of the United States. We have a strip here through Texas. We have a little bit in West Virginia, but much of the eastern half of the United States is much, much cooler. So even if we drill down quite deep, 6.5 kilometers, you're still seeing temperatures of 100, 120, 150 degrees Celsius. That's 200, 250, 300 degrees Fahrenheit. That's really not even hot enough to produce geothermal power. So that's why geothermal is localized spatially in some places more than others. Now, what's interesting about this plot is Essentially, if you're at about 175 or 200 degrees Celsius or higher, that's hot enough to produce electricity. And so what this map is showing is that you could pretty much go anywhere uh, west of the Rockies, with a few exceptions, and drill a well down to this depth, and it would be hot enough to produce geothermal power. So then the next question is, well, great, why don't we just do that? Why don't we go anywhere in Nevada, just start drilling wells, and we'll produce geothermal power? It gets back to this topic of flow rate. So not only do we need to drill a well, but we need to drill a well into a formation where there's a very high capacity for high flow rate. That doesn't exist in most places. In most places, if I just went into the middle of Nevada, randomly drilled a well, there's a good chance that I would get very little water to flow out of it because of the just conditions of the reservoir of the rock at that depth. So that again is the limiting factor traditionally for geothermal has been the availability of resource. And I'll talk about in a moment technologies to try and address that limitation. So in the United States, the majority of electricity production is coming from geothermal electricity production is coming from California. Nevada is number two, and there's not a huge amount anywhere else when we talk about electricity. When we talk, in fact, let me show you where that is happening. So the geysers here in California, this is near Santa Rosa, so north of the Golden Gate Bridge. Beautiful area. This is the largest geothermal field in the world. That's what it looks like. So that's the cooling towers. They're evaporating water as part of the power plant. And here are some of the wellheads and some of the pipes that are bringing the fluid into the power plant. This is Coso Geothermal Field. This is kind of south of Bakersfield, kind of northeast of LA. This is actually on a naval weapons testing base. Just so happens to be a very volcanically active area, and they have really excellent geothermal resource here. So that's what this looks like. They have recent surface volcanism. So if you walk around out there, there are chunks of obsidian on the ground. So you can see, this is obviously kind of a special place. And then Imperial Valley is near the border with Mexico. Very, very hot, very unusual type of geothermal reservoirs because it's in sedimentary rock. This is unusual because also it's extraordinarily corrosive fluid that they produce out of the ground, and actually have to use titanium casing and do other sorts of very specialized things. So again, just kind of emphasize you need special geologic conditions. Direct use is much more broadly applicable. So this table is showing all the different places across the US where different direct use applications are being found. And for example, Oregon is a major adopter of direct use, even though they're not a major adopter of electricity generation. The same thing for Idaho. Yeah, so this is the shallow ground source heat pumps I referred to. This is just for building heating and cooling for residential, things like that. Yeah, so that's kind of an overview of conventional geothermal. So, and I talked a little bit about this direct use versus electricity. Direct use, basically, when you have lower temperature, that's when you're going to do direct use. When you have higher temperature, that's when you're going to do electricity. Finally, I want to talk about enhanced geothermal systems, or sometimes called EGS. So that is the use of hydraulic fracturing or hydraulic stimulation to improve the flow rate of a geothermal well. So back to this plot here. This plot is incredibly kind of alluring because what it's showing is that the size of the potential geothermal production is very large. It's saying that the state of Nevada represents, anywhere in the state of Nevada, represents a reasonable drilling target for geothermal if we could get the flow rates high enough, right? So anywhere in Idaho, most of Oregon, much of California, much of Utah, New Mexico, Colorado. That's what we're seeing here. And even places in Texas and in West Virginia. So then enhanced geothermal systems is saying, all right, well, we're going to figure out how to go somewhere where there is temperature available, and we're going to use hydraulic stimulation or hydraulic fracturing to increase that flow rate. So how do we do that? Well, if you guys are familiar with hydraulic fracturing in general, you probably are. So in hydraulic fracturing, we inject water and we inject sand into the ground, and that injection of water, it cracks the rock. We're pumping sand into those cracks that holds the cracks open, and that creates these pathways for flow through the solid rock. That, of course, is very widely adopted in oil and gas. It's foundational to the unconventionals business. Certainly in the Northeast, you have Marcellus, Utica. Those formations are being produced from hydraulic fracturing. So, of course, hydraulic fracturing, the geothermal people are aware of the concept. And in fact, it has been attempted since the 1970s. So enhanced geothermal systems means we're going to use hydraulic fracturing to increase the flow rate achievable from geothermal wells. If this can be done consistently and for sufficiently low cost, there could be enormous growth in geothermal electricity production. Because instead of on this map being localized to special little dots where there's very, very special permeability accumulations, but actually we could just go to a much broader set of places and drill and fracture and produce power. So that's why enhanced geothermal systems is so attractive. This was first tested in the 1970s, and it has not become widely adopted. So we should ask, we've had 50 years. Why is it that after 50 years, EGS still has not become widely adopted? And what I would say is there are reasons for that, but in the last 5 years, big changes have happened and the performance of these wells has shifted dramatically. And so the perception of enhanced geothermal systems has shifted dramatically, and that makes this a very exciting time. So EGS has been attempted since the 1970s, and typically projects have not achieved sufficient flow rate. So we're trying to use fluid injection to create stimulation and increase the flow rate. It's worked okay, infrequently, right? It's not reliable, it hasn't been effective. Or it's been moderately effective sometimes. What we need is very effective all the time. And so what engineers over the last decade started saying is, well, hold up. The way that people have been doing hydraulic stimulation and geothermal is very different from how it's being done in oil and gas. And what's being done in oil and gas is working very, very well. And so the approach is to move away from the hydraulic stimulation approaches that were used in geothermal for many decades and adopt a much more oil and gas style hydraulic stimulation. And in fact, that has been now done in the last few years, and in fact, it has worked very, very well. So first, let me start with the old approach. The old approach here was to pump only water with no sand, and they would pump water down into the ground. Then they would stop pumping and hope that there was a good flow rate. This plot on the right here is quite interesting. So this is a vertical well. It's from the Sults project that was done in France about 20 years ago. And they injected water at high rate into this well. And then they ran an instrument into the hole that actually spins, and it can measure how quickly the flow is happening through the well. And what we see is that most of the flow is exiting the well at one location. And all of the flow is happening at only 4 locations. When they stop pumping, most of these fractures close off and they get an okay production, but not enough. So that's not enough flowing pathways. In other words, this is half a kilometer of well, and they have only 4 places where flow is happening. So what's the approach that we should do differently? Well, instead, we should do oil and gas style hydraulic fracturing. So that has been attempted by both the company Fervo and also by a DOE funded project called Forge. And in both Fervo and Forge projects, performance has been dramatically improved by the use of oil and gas style stimulation. So I will explain what that is, but first let me just kind of show you the results. So this bar chart is showing a variety of different projects from the 70s to the 2020s. And it's actually showing the best projects. So these are the most successful EGS projects. And on the y-axis is the flow rate. So that's in liters per second. 30 liters per second is actually quite a lot. It's 15,000 barrels per day. But that's still not enough. Generally, we think that economic production is going to need 100 liters per second or more. It's typically viewed as the target. So for 50 years, this is just a subset. There are dozens and dozens of projects attempted. None of them did better than 30. Then Fervo came along, and in their first commercial well, or pair of wells, they adopted more modern stimulation strategies. And in their first try at Project Red, they doubled the flow rate that was the best ever prior to their project on their first try. On their second try, that was the Project Cape project, they got another 50% improvement, and they more than tripled the best ever. So there is no question now, it has been demonstrated that adopting these modern oil and gas stimulation treatments does result in dramatically improved production. And that's critical because everything is about revenue, right? We have to spend millions of dollars to drill these wells, and the way that we're going to pay for that and the way that this is going to be an economically viable activity is if we can produce enough electricity to sell that electricity to pay off the well and make a return on investment. So if you spend a bunch of money and you get a certain amount of power, well, let's spend the same amount of money and get 3 times more power. That's 3 times more revenue, right? So the cost per kilowatt hour has shifted dramatically as we've seen these improvements in flow rate. That's from oil and gas style stimulation. At the same time, they've also been able to dramatically improve the drilling performance. So drilling geothermal wells was traditionally much slower than drilling oil and gas wells. And the geothermal old hands would tell you it's because, oh, it's just harder to drill a geothermal well. Well, turns out that if you get best practice oil and gas drilling techniques and you apply those to geothermal, you can drill a lot better. So over here on the right, sorry, this is a bad picture. I took this as a screenshot from a presentation. But they're showing how, as they adopted new drilling techniques, they were able to cut their drilling times by literally like a factor of 3, 4, 5 relative to what is a traditional geothermal drilling time. So drilling time is one of the main drivers of cost. So what we're seeing is that cost is dramatically dropping while revenue is dramatically improving. And the consequence is that this activity of using stimulation to improve geothermal production, even 5, 10 years ago, that looked really out of the money. Suddenly the costs are maybe not competitive with natural gas, but are a lot closer to natural gas and they're within spitting distance. And so when we consider that geothermal energy does not have associated greenhouse gas emissions, also it is a baseload power source, so it is not intermittent like wind and solar. So those advantages may justify paying a few extra cents per kilowatt hour. And that's what Fervo is banking on, and they're banking on they can continue to do this. All right. So what is the insight or the shift in design that was achieved? Well, this is getting pretty nitty gritty, but this is how we do it in oil and gas, and this is what Fervo has done. So we'll drill a horizontal well, and then this well will be full of steel pipe, and we'll cement the steel pipe into the ground. Then we will make some holes in the steel pipe towards its toe. That's the bottom of the well. And we're going to pump water and sand out of those holes. Once we're finished, you set a plug. You actually just isolate what you just pumped into, and then you make more holes and you pump again. So you're able to pump into this section, then this section, then this section, and then this section. You can do that 20, 30, 40, 50, 60, 70 times up a well. And every single time you do that, you make a lot of new fractures. So consider within a stage, you might have perhaps 10 different places where you're able to inject fluid out of the well and create fractures. You might have 50 stages, which means you're able to make 500 discrete fracture flow pathways along the well. And actually, evidence suggests that you really may make even more than one fracture per perf cluster. So you're making at least 500 fractures along the well. You can compare that to this example. This was the 20 years ago stimulation design. They have 4 flowing pathways. So we're taking stimulation designs that used to result in about 4, let's say 1 to 6 flowing pathways. And now we're moving to stimulation designs that can create 500 and perhaps 1,000 flowing pathways. So this multi-stage hydraulic fracturing approach, that is extraordinarily successful. It's what's transformed oil and gas and is promising to do the same for geothermal. Another big shift is the use of sand. So traditionally in these in these geothermal stimulations, traditionally they did not pump sand. They relied on the hope that the fractures would kind of hold themselves open. But it turns out that that's not very reliable. And when you pump sand along with the stimulation treatment to hold the fractures open, you can get dramatically improved performance. So this is kind of a simple simulation. It's actually a numerical simulation with kind of an idealized geometry showing what this can look like. So we've drilled a well down here. It is vertical right there, and then it cuts horizontally. We've drilled another well over here, and it's also cutting horizontally. So you have 2 wells. They're both going left, right, and they're parallel to one another. Then we use stimulation to create a large number of these fractures, and then we can inject down this well. It heats up as it flows through the rock, and then it reaches over here to where this production well is. And so as we inject cold water, it heats up as it flows through the rock, and then we produce the hot water surface. And the consequence is we have a well that's perpetually producing a high rate of hot water. That can be used to generate electricity. That process extracts heat, so we actually lose temperature, and we re-inject again with a lower temperature. So we have a cycle, and I think this schematic is pretty good at showing how there's an injection well, the fluid goes down, it heats up in the formation, it comes up, it goes into the power plant, we sell the electricity, the fluid cools down, and then we re-inject the cooled fluid. So that cycle of fluid production, injection over and over again allows us to extract the heat from the formation and generate electricity. So that's a pretty cool thing. So Project Red, this was Fervo's project, their first project in Nevada. As you can see, there are two wells. They drilled them down about 7,500 feet and then kicked them laterally by about 3,000 feet. They're actually over here on the edge of an existing geothermal field. So there's a power plant over here already, but it's in a part of the formation where the reservoir, where the rock is not very permeable. So it had been difficult to get productive wells drilled over there. So they were able to stimulate those wells. I won't go through this figure, but they got good frac data. The fracture was successful. And ultimately, as I mentioned, they got very high flow rates. They also they ran that spinner log. They can see where the fluid is exiting the well, and what they can see is they have a nice uniform distribution of flow across the well, which is quite good. So they've actually been producing that well for several years, and just today, they posted this article. Actually, I was just looking at it right before this call. So this is dated today, April 13th. Enhanced geothermal has been proven at scale. Here's what 2 years of production data show. So this is what Fervo just put out, and that Project Red doublet. They're showing here, this is the production rate in orange and the production temperature in red. And they're showing that they have been able to produce this system for a while with modest thermal decline. Now, there is eventually going to be thermal decline. So there is a finite amount of heat in the rock, and over time, that rock is going to cool down, and they're going to eventually have a production temperature that's too low, and they're going to have to stop producing. But haven't gotten there yet, so they're cruising along pretty nicely there. So very exciting to see that, and it's really quite revolutionary. Also want to mention this Utah Forge project. This is a Department of Energy funded project. It is also pursuing, they have drilled two horizontal, or rather highly deviated wells, performed oil and gas style multi-stage stimulation. And they are actually next door to Fervo's second project, which is called Project Cape. So this region near Milford, Utah, in kind of southwest Utah, is hosting both the Forge and the Fervo work. And this project has still kind of in progress. I'd say that it is going a little slower because it's more of a science project. So they've been trying a lot of different things, very good at publishing. So they've made a lot of important developments and popularized learnings around drilling improvements. We've seen different things from stimulation. There's been excellent data collected on the stimulations and the flow behaviors. In fact, I personally am working on a study right now where we're trying to analyze the data from the Utah Forge project. So this has been very, very valuable. The slide's a little out of date. It says from 2 weeks ago, but I'll just say flow tests reached. Flow tests reached 33 kilograms per second. So their flow rates are lower than some of the stuff that has been reported by Fervo. But also they've actually stimulated only a much shorter section of lateral to date. So in the long run, when they've stimulated the full wells, they expect even higher flow rates. So this is really exciting stuff. It promises to bring things into cost parity or cost competitiveness between geothermal and other forms of electricity. And then there is a very large resource available here. Very, very exciting stuff. All right, so I also want to talk about induced seismicity. It's an important topic, and it's something that we need to be, conscious of. So induced seismicity is the idea that when we inject or extract fluid from the subsurface, it has the potential to trigger earthquakes. And this is something that's, I think, already known in kind of the public, discourse. You might recall several years ago, there were a lot of wastewater disposal wells near Oklahoma City that caused induced seismicity. That was not something they were used to. Today in West Texas, there is some induced seismicity also believed to be associated with wastewater disposal wells. And even in geothermal, even conventional geothermal has traditionally probably had some induced seismicity associated with it. So one thing that happens is when you inject fluid, you increase the fluid pressure in the ground. And so that has the potential to cause earthquakes by causing fault slip. Um, Injection of fluid is certainly what we're going to do during these stimulation treatments. So when we do hydraulic fracturing, either the oil and gas style method or the geothermal method, both of these techniques involve injecting water. If that water gets into faults, they have the potential to induce slip on the faults. Um, there are actually a lot of other human activities that can cause induced seismicity. Actually, any fluid production has at least some potential to cause induced seismicity because of the volumetric contraction of the reservoir. And actually, interestingly, the construction of dams and surface water reservoirs, man-made lakes, actually that has been associated to some of the largest instances of induced seismicity because what it does is basically change the weight of the crust and it redistributes stresses in the subsurface. So actually, there are a lot of things that have historically been identified as potentially causing induced seismicity. But in particular, it's happened from time to time with geothermal energy. So this is something we have to keep a close eye on. Obviously, we're excited about the potential, but we need to do this responsibly, or else if we're causing, meaningful induced seismicity, it's going to be a significant issue for the, for neighbors and for these projects. So first off, how does this happen? Well, this schematic is kind of showing it. This solid line here represents a fault. So I think you guys are probably familiar with what a fault is. It's kind of a crack in the subsurface where rock can slide along that fault. That's how earthquakes occur. And those faults are kind of always poised to slide, except that friction is preventing them from sliding. So friction is happening because of the weight of the rock above. So let's say you go down 5,000 feet, there's a crack in the rock 5,000 feet deep that might hypothetically be able to host fault slip. One reason it may not is because the weight of the rock is so strong, it's squeezing down on that crack and kind of just preventing it from being able to slide. But that's called a normal stress. So the normal stress sigma n is the squeezing on the rock or on the fracture created by the weight of the rock. But resisting that friction or resisting that normal stress is the fluid pressure. So there is also some fluid inside of the fault, and that fluid is pushing outwards. So at the same time the rock is pushing in, the fluid is pushing out. And so if we inject water, we increase the fluid pressure from injection, then what we're doing is we're causing more kind of outward pushing, and we're going to weaken the friction that is on the pre-existing fault that's preventing it from slipping. And that's captured by this equation called the Coulomb failure criterion. So that is sort of the fundamental concept of how induced seismicity could occur. And furthermore, if we removed or otherwise cause sorts of distributions of stress in the subsurface, it can affect these stress terms, and it has the potential to bring the crust closer to failure in some places. Now, having said all these things, most of the time, by far, we do not have induced seismicity. So why do we not typically see induced seismicity? One reason is that a lot of slip that occurs on faults is not causing earthquakes. So an earthquake happens when there is rapid motion on a fault. So a fault is stuck, and then all of a sudden, quickly within a second, it slides. That usually doesn't happen. So most of the time, when you have a pre-existing crack deep in the subsurface, it's actually just going to slowly slide, and it's going to be able to deform and accommodate deformation, but it's not going to happen quickly, and no one will ever notice because it will not cause vibrations. It will not cause an earthquake. So that's one point, is that most fault slip is what we would call aseismic. It just doesn't create earthquakes. It happens, doesn't matter. Another reason is that the fault may not be that close to slipping, or it may not be that big. So if you have a very small crack, even if you did inject into it and it did have a little bit of slip, it would be so tiny that you'd never feel it. And in fact, that's actually the case. So we have a term called microseismicity. Microseismicity refers to micro earthquakes that humans can't even feel. So if it happened right under your feet, you would never know. But we can put out very sensitive seismometers, which have the ability to measure these sorts of very, very small deformations. So microseismicity is very common from fluid injection. Felt seismicity is much more uncommon. Now, one other kind of concept in induced seismicity is that the magnitude of the earthquake you might potentially induce is determining kind of how much change you're causing. So This is a plot of basically all of the worst induced seismic hazard or induced seismic events in history. So Art McGar, he did a review, and if we look at these dots, these larger events, they actually have nothing to do with geothermal. They have to do with actually all the big ones have to do with the construction of his dam. There's one dot up here that is possibly induced and is related to oil and gas production in a very specialized circumstance. Um, but when we talk about induced seismicity from geothermal, we're lower down here. But it really has to do with the size of the perturbation. So there's different kinds of things that people can do to look at in the uncommon cases when induced seismicity has happened, try to understand why and how to quantify that. And that has led into what we call the induced seismicity protocol. So this was a protocol developed by these experts down here on behalf of the Department of Energy. And they have a very systematic procedure that they've laid out for how to assess risk and site selection. Hey, should we not do this here, right? So would I recommend drilling across the San Andreas Fault right under San Francisco and pumping a huge amount of water? No, I don't think that's the right site, right? So there's a site assessment of hey, is this a safe place to be doing activities? And then there's a variety of other parts of this methodology. So for example, once the assessment is performed, once activity has started, monitoring, and generally what's happening is if there's more induced seismicity than you might expect, it's going to kind of start small and build. So you can identify that and you could terminate. So there's something called the traffic light system where you would stop activities if things kind of looked like out of the ordinary. So for example, here's the results from the traffic light system from Fervo's Project Red. So what they had said is, hey, if there's anything larger than a magnitude 2, we're going to call that a yellow. And if there's anything larger than a magnitude 3, we're going to call that a red. So in advance, they defined certain kind of stopping criterias and procedures. So they monitored during the stimulation. And I'm sorry, this was Project Cape, not Project Red, Project Cape in Utah. And as they did these stimulations, each one of these dots is a seismic event. So they stayed within the green region the whole time. But if they had gone to yellow, they might have backed off a little bit and then resumed. So this is the traffic light system. So this is all part of these procedures to try and kind of relate activities and monitor and make sure we're being safe. Another topic here is related to hazard and risk. So hazard refers to the idea that, hey, can we induce a seismic event? Risk is a word that refers to the idea of how will that impact people. So for this particular project, Project Cape, what they're showing is, oh, you know what? I'm sorry. This is actually his Project Red. This is Project Red. It says Nevada here. So what they're saying is that the closest human habitation to this well was about 35 kilometers away. So they said, all right, well, what if we did induce? Okay, so their threshold here for stopping was a 3, which is actually smaller than this yellow line. So they're saying, all right, what if we did induce a 3.5, which is above their threshold for stopping? Even if they did, what they're seeing is that there would be very light shaking within 5 kilometers, and there would be nothing felt in the closest human habitation. So that's also part of the process of seismic hazard assessment is, it may be that causing a 3.5 truly nowhere near any human habitation is a low risk activity. But if you did it directly underneath the city, there are just so many people that might be potentially affected, either from the nuisance point of view or just the statistical odds that it cracks somebody's foundation or damages a roofing or something is greater. And so that's part of the assessment as well, both hazard and risk. Fortunately, most of these projects are located not in the middle of cities. However, the two instances when induced seismicity has been an issue for EGS have both involved projects that were pursued directly underneath cities. And I think that's a good lesson that EGS projects probably shouldn't be getting done directly underneath cities. So this Pohang project is a bad example. So this was a project in 2017. This was in South Korea. This was not using the modern oil and gas style stimulation treatments, but was using the older style of stimulation treatment. This was directly under the city of Pohang. And evidently what happened is that there was apparently a very large fault, and that large fault was near the well, and it was already poised to have an earthquake. So actually, we would call this a triggered event in the sense that if they had not drilled this well, that earthquake would have eventually happened anyway. Now, having said that, that earthquake might have happened in 300 years. So just the fact that it was kind of, you can say, yeah, it would have happened anyway. But if it would have happened in 300 years, well, from the perspective of anyone impacted by that, it was caused by the injections, right? So, in this case, whatever it was, there was a natural fault that was poised to have a seismic event. They managed to drill or they injected a lot of water at very high pressure straight into that fault or right next to that fault. And it triggered a magnitude 5.5, which is by far larger than any induced seismic event that ever seen before or after from an EGS project. So they did not follow this procedure. They did not map that fault. They did not, do all the right things they should have done. Also, they used extraordinarily high injection pressures, which was also quite unusual. So, I think that this is definitely a cautionary tale for the space of EGS and geothermal generally. This doing best practices is critically important. Consideration of things like hazard and risk, what is this site and what if there was a magnitude 3, what would be the impact? That's all part of this. But yeah, overall, it's a very exciting area. We have to pay attention to these topics, obviously have to do this responsibly. But the potential is very exciting. The potential is we're seeing extraordinarily high flow rates. We're seeing excellent drilling data, which means that this is becoming something that's economically viable in the near term. Fervo Energy in particular, what I read in the news is that they're planning to IPO this year. So that's pretty wild, pretty extraordinary. I've known those guys who founded that company since before they founded it. It's amazing to see what they've been able to build. There are now many other companies who are looking at pursuing similar approaches. My own company called ResFrac, we help companies design hydraulic stimulation treatments. We help them design EGS systems. And what we've seen is a tremendous growth in interest from our customers and from new people who have come in and wanted to use ResFrac for designing these sorts of systems. So definitely it's an exciting time. From our point of view, the engineering is very interesting, all the different decisions we have to make about how to optimize these systems. We're working really hard with these operators, the ones who are going out and taking the risk to hopefully help this field grow more. So I will pause and take some questions.
Thank you so much, Mark. That was super interesting, and we did get a bunch of questions, so we'll try to get as many in as we can. So once we have the heat or power, how do we get that power to where it is needed?
Yeah, well, so power, the power plant is going to need to be pretty close to the wellhead. Now, what Fervo is doing is pretty great because they're drilling down and then laterally. So they can drill like 12, 16 wells from a single pad. And then the pad, like the actual wellhead, is directly adjacent to the power plant. So that's actually really convenient. Of course, once it's in the power plant, we still have to sell the power. So I'll get to that in a moment. If we look here at this picture of the geysers, these wells are more spread out. And so they have to have these pipelines all over the place that are kind of collecting in produced hot water and steam to get into the power plants. So that's step one, is just getting the hot water and steam into the power plant, which is not trivial, right? Then point two is we've got to sell the electricity, obviously. So yeah, it's a big deal. I mean, if you're truly in the middle of nowhere, building a power plant or power line out there is not a negligible cost. And so that is significant. I think when people are looking at site selection for these projects, they're not just looking at these temperature maps, but they're looking at maps of the power lines. The Project Cape and Forge, they are very close to a very large power line that's running into Salt Lake City. And so that's a big advantage for that site. So that's a part of it. Also, there are practical problems. I'm told right now there is a huge backlog on getting hold of transformers. So in order to literally get the electricity from the power plant into the actual power line, you've got to have transformers. And I'm told there's a massive shortage across the country, and that's creating large delays in terms of people sourcing those. I imagine with supply and demand over time, that should clear, but the next 2 or 3 years are apparently very, very tight. That's not caused by geothermal, of course. It's caused by the demand coming from data centers, which is creating a huge surge in transformer demand. So it is a big deal. It does need to be, a strong part of site selection is determining where the market is. Another thing about the market is what price they're willing to pay. So California, very aggressive CO2 emission reduction targets. they're going to pay a higher price than other states, right? So that's part of it too. You asked about direct use. Yeah, so for direct use, that's hot water. So, you just can't pump hot water that far. It will cool down, even if you have an insulated pipe, and insulation's not cheap, right? So, generally speaking, a limitation for direct use is you need the demand source to be close to the wellhead. And of course, even if you did have a nice warm place somewhere in the middle of nowhere, you don't necessarily, that's not the place where you need space heating, right? So that's one of the challenges is kind of finding places where the heat resources can be co-located with the demand source. And that is one of the limitations to direct use.
Thank you. What does the environmental permitting look like for these projects? And is there any ongoing monitoring?
Well, there's definitely ongoing monitoring. There's no question. There's a lot of monitoring of everything that's going on, both from the induced seismicity perspective and everything else. The permitting processes are protracted. I don't work for an operator. I can't say I'm an expert on the permitting, but it takes them years. It's worse in some states than others. I'm told that in California, the oil and gas wells are taking years to get permitted, and California is speeding that up for the geothermal people. So it's better for the geothermal people. But yeah, it's a very, very, very strenuous process. I remember the Forge project. They decided to drill the well in a different location, and it took 6 months because somebody had to go out and walk around and look for archaeological artifacts that might be on that site. So there's 6 month delay just from the archaeological review. So there's a lot to it, and it creates a lot of project timeline stretch.
Is there a Fervo project in Germany?
No, there is, well, there have been dabblings of geothermal in Germany for many years. But geothermal remains quite, low adoption in geothermal in Germany because it's actually not a very hot place. There's not a lot of volcanoes in Germany. There is one high profile project from a company called Ever, EAVOR. They are a Canadian company, have a lot of funding from the Canadian government. They also got a lot of funding from the German government to go out and drill some wells in Germany. They have a different approach than what I've been talking about. I'm not a big fan of it, their approach. In fact, I'll go back to this slide. Deep closed loop heat exchangers. I am a skeptic. So I didn't cover that. But this company Ever does deep closed loop heat exchangers, and that's what they did in their project in Germany, which is perhaps what you are referring to. So in these deep closed loop heat exchanger projects, there's no fluid that goes in or out of the well. So as we see in this schematic, the fluid goes down the well, it flows through the rock and flows back up again. In the closed loop projects, they just circulate fluid through the wells only, and they don't have fluid leaving or going into the wells. That doesn't produce a lot of power. So, and that's pretty easy to show kind of mathematically. So that project in Germany from Ever, they have spent years. They had the two biggest drilling rigs in Germany for years, drilled a ton of wellbore, and it is producing a very, very low amount of electricity right now. So I was talking about how in enhanced geothermal systems, there's been dramatic improvements in cost per kilowatt hour. The deep closed loop concept, it has attracted some attention and funding, but to date, it is much more expensive. I mean, more than an order of magnitude, maybe 2 orders of magnitude more expensive. And so personally, in the absence of really kind of just total change in cost structure for things, it's hard for me to see how that's going to scale. But others have different opinion. It is attracting funding out there. Yeah.
Thank you. In general, how would you compare and contrast the differences between the risk and seismicity management around EGS and CCS?
Oh, that's a very good question. Yeah, they are different in different ways. So I can give you some really specific answers. So I'll say why CCS is going to have a lower hazard, and then I'll say why it'll have a higher hazard. So for lower, the tendency for seismic or aseismic slip depends on the type of rock and what's actually in the fault gouge. And so when you inject fluid into sedimentary rocks, there are usually a lot of clay-rich formations around, and that clay has a tendency to smear into faults. So the vast majority, 99.999% of faults in sedimentary rock are not hosting earthquakes. That means if we're doing CCUS in sedimentary formations, we're going to be safer just off the bat because we're probably injecting into kind of areas where the faults aren't going to cause earthquakes, even if they did slip. Now, having said that, when we look at situations where wastewater disposal has caused induced seismicity, that's usually been because the wastewater disposal wells were sitting in the sedimentary rock right above the crystalline basement. So now let's talk about the crystalline basement. Below the sedimentary rock is granitic rock. That's just kind of cooled magma that's much older, been there for a long time. So if you go deep enough, you always reach the crystalline basement. That's where most geothermal wells are. So EGS has had a higher incidence of induced seismicity than CCUS because it is in a different type of rock. That crystalline basement is more likely to have induced seismicity. So that's good for CCUS. On the other hand, CCUS, if fluid pressure gets down into the crystalline basement, you can still induce seismic events there. That is, in fact, what was happening in Oklahoma City. Um, then on the bad side for CCUS, the volumes are much larger. So when we talk about CO2 sequestration, you're putting very, very large volumes of fluid into the ground by design. And as we see from this diagram, the larger the region of perturbation you create, the larger the maximum magnitude becomes. So this is I think, a significant issue for CCUS, and it's something that, for example, Zobak and Gorelick had a paper about this 15 years ago, saying, hey, you're going to create very large regions of pressurization. That does pose hazard risk, and in some sense, the maximum magnitude is much worse for CCUS. My personal opinion, CCUS should be done only in depleted reservoirs. So if you go to a depleted oil and gas reservoir, you've already brought the pressure down. So if you brought it back up again, you wouldn't be kind of going past where it was before, and the induced seismic hazard would be much, much lower. Also, it's just easier to inject into a depleted oil and gas reservoir because the fluid is more compressible. But if you go to a saline aquifer, that is actually a very low compressibility system. You're going to have to pressurize vast regions of the subsurface to put away significant volumes of CO2 in water, as opposed to injecting back into oil and gas reservoirs. And that is going to have meaningful impact on the induced seismicity hazard. It's a real issue.
All right, we're gonna end with one last question. There are a ton more, but to be respectful of everyone's time, what is the risk of contamination of groundwater supplies when using the newer practices?
Yeah. Well, I mean, first off, I don't know of much groundwater contamination that's happened from hydraulic fracturing, period. But secondly, you're not producing oil and gas anymore. So, I mean, if you're concerned about that, you're injecting water, you're producing water. In terms of the fluids used from hydraulic fracturing, again, the chemicals that I'm aware of are not much. Actually, it turns out that the more complex chemicals that could be used for hydraulic fracturing are expensive and they're not even useful. So the fracturing fluids that are being used for these geothermal wells, as well as the vast majority of oil and gas wells these days, are actually just water with a little bit of polyacrylamide in it, which is not a toxin at all. So essentially, the frac fluid is a relatively benign thing. And then you're producing water from the ground. So in that sense, both of those are limited. But again, just to put this in context, these wells are drilled thousands of feet, miles deep into the ground. The groundwater is within the first few hundred feet. You have multiple layers of steel and cement between the inside of the well and the formation. So the incidence of leaking wells is rare. And when it's happened, it's old wells. Newly drilled wells are not leaking into the groundwater at all. And I think it's a very limited issue. But if that's something that worries you, you can at least be satisfied that the geothermal stuff doesn't involve oil and gas and involves very simple fluids. We find that simple kind of benign fluids are actually more effective anyway, and so there's been a big shift in the industry because of that.
Well, thank you so much. On behalf of the TOPCORP team and everyone attending, I think we have learned a lot. We'd love to see you back again soon. And thank you everyone for tuning in. See you all again
Absolutely.
soon.
And feel free to reach out to me. Here's my email if you have any questions. Always happy to chat with people. Thanks for joining, guys.
Fantastic. We'll send everyone the recording in about 3 business days. Thank you.
All right. Take care.